Okay. So to do that, the first thing I want to show you is that let's define J as dV, that's little v, over dV0. So this is the reference, the current configuration volume over the reference configuration volume of all constituents, right? So this J is like the J of the solid skeleton and the pore space, right? So we're not making any distinction on, J of S or J of F for that J, right? That is the total J, if you will, or the J of the solid skeleton, right? Okay? Let's define J bar as dV S over dV S, right? So this is the volume of the solid in the current configuration divided by the volume of the solid in the reference configuration. Okay? You can also show that this is equivalent to V bar S V bar S 0. All right. Then we also had that the volume fraction, phi of S, is equal to dVs, so the current volume of the solid divided by the current total volume, right? From the definition of the volume fraction constraint. And just given the definitions above, we could express this as J bar dV0 S J dV0. Likewise, we have that the reference volume fraction is equal to the volume of the solid in the reference configuration divided by the total volume of the reference configuration. And so combining all those equations, we can get that phi of S is equal to V of S over V0 S phi 0 S J, or we could solve for the term V bar S V 0 S. We can solve for that in terms of J. So, see if I can get it all on the same screen here. All right, so you see at the top of the page there, we also have the J of S. Remember, that's our conservation of mass we've been working with. And look at the far right-hand term. You have V bar of S over V0 of S, right? So if I substitute in this guy right there in that term, then I have J of S equals J times phi of S. But look, there's a phi of S in the denominator. And phi reference of S, there's a phi of reference of S in the numerator. So those terms cancel, right? So that ultimately we get J of S is equal to J. All right, so what that says is that the determinant, J is a measure of volume change, right? Finite deformation volume change. what this basically says is that J of the solid skeleton is equal to, I'm sorry, J, just the plain J, is the J of the solid skeleton as we defined it. It's equal to J of S. Right. So they're equal. So basically what I'm saying is everywhere there's a JS, I can replace it with J. And that's going to come in handy in just a second. Okay? So we have this. And then the other thing is, in mixture theory, we have the total stress is equal to the volume fraction of S times what I'll call sigma bar S ij plus the volume fraction of the fluid times the fluid stress. So these bar terms, so it's called the intrinsic stress. Intrinsic stress. This is the stress that component, the alpha component, would feel if it's isolated, right? Okay. So what I'm going to do is I'm going to solve this equation for the solid intrinsic stress. Or I should just say rearrange this equation. And now the total stress, I'm gonna plug in the total stress that we derived here. This guy. That's the total stress. Right? Oh, let's see. Yeah, I want to do it in the current configuration. Okay? So then I have now I'm going to plug in, remember, we have the volume fraction constraint, which tells us that the volume fraction of the fluid is 1 minus the volume fraction of the solid. Right? So I'm going to plug that in there. Then, since we know that that P, we know that P is the Lagrange multiplier. We know that worked out to be the thermodynamic pressure of the fluid, right? So what we're going to use then for this fluid stress, we're just going to say that the fluid stress is equal to minus P delta ij, so it's acting isotropically, right? And just based on the definitions we've been using, it's positive. It's the value of P is positive in compression, right? So then the total stress, we have to put a negative out there, because we're about to use a constitutive model, and everything else we've done with the traction vector on the skeleton and all that is positive in tension, right? So basically, the other thing we're going to do is we're going to say, we're going to use our constitutive model, sigma double prime of S, ij, we're just going to make that equal to a linear elastic isotropic solid. So we're just going to use generalized Hooke's law for an isotropic solid. Where, okay, so now we're talking about small strains. So this is a small strain tensor, and G is the shear modulus, and K is the bulk modulus. All right. So now we're going to plug that in and this into that equation. Okay. We're going to plug it in. So I don't know. I'll call this star and star star. So plug in star and star star and evaluate at I equal to J. So then we have sigma I double prime of S is equal to K minus 2/3. What is delta II? 3. Right? It's the trace of the Kronecker delta function. Kronecker delta function is like an identity matrix, right? So it's 3. So use that thing. Now notice there's like a minus 2g sigma kk and a 2g sigma kk, right? So this results in 3k this should be, I'll just rewrite it, phi of S sigma I double prime of S. All right. Now I'm going to divide both sides of the equation by minus 3 phi S. So what I'll get over here on the left is minus 1/3 sigma kk double prime S is equal to minus k over phi of S sigma kk minus 1 over phi of S 1 minus b times p plus p. And this thing over here on the left, by definition, we're going to call P bar of S, just using our standard definition where we've called, the pressure of a solid, or the pressure of a solid, but now we're talking about the intrinsic solid, right, is equal to minus 1/3 sigma kk. What's that? Yeah. So we're basically just using our standard definition of the hydrostatic stress, or the pressure, right? Basically just replacing that symbol for that, right? And then what's on the right-hand side is the same, right? But basically what this shows us is what the intrinsic pressure is in the solid. Okay, now we already used the small strain constitutive model, but let's look at another, because basically what we're trying to get after is the linearization of the Biot coefficient. Okay, so we know this is the intrinsic pressure, but there's a couple other things that we know under small strains. Under small strains, we know that sigma kk, epsilon kk, is approximately equal to J minus 1. We know that the current volume fraction is approximately equal to the reference volume fraction. And we also know that the current specific volume is approximately equal to the reference specific volume. Under small deformations. So let's plug in these first two things into that equation. All right. Now, we sort of, there's a J in this equation, right? So we could solve this equation for J in terms of P bar, right? So J, given this relationship, J is a function of P bar, right? So J is a function of P bar, yes. So given that, let's go back to our Biot coefficient. B is equal to 1 minus 1 over now remember originally I had a JS there. But we also just proved that JS is, anywhere that's a J, I can replace it. A JS, I can replace it with a J, right? So I'll just make this J. Well, since we know J is a function of P, we can say 1 recognize, right, rho 0, well, 1 over V0 is equal to rho 0, right? S, right? And rho 0 is equal to that, right? And then that is equal to that, just using the definitions that we already have. Right? So I have okay, so all I did there was, remember, this is under small deformation, this is approximately equal to those two things are approximately equal under small deformations, okay? So, and then according to this equation, J is a function of P, so that I can use a chain rule here, partial Vs, partial Ps, partial Ps, partial J. Now this thing here is by definition the compressibility, or 1 over Ks, the bulk modulus of the solid. It's actually negative according to the common definition, right? But this is right? That's the definition of the bulk modulus of the solid. It's a common definition. Right? So basically I can replace this term with 1 over Ks. Right? There's a minus sign out front. Right? Now this guy we can compute from the constitutive model. Right? So yeah, I mean it's only a constitutive model because we substituted in generalized Hooke's law, right? But I mean, no one, there's not a mechanician on earth that's going to call foul on that, right? I mean, it's like the common generalized Hooke's law is the common definition, right? So what we have now is then partial P bar of S partial J is equal to minus K phi 0 of S. And, you know, we're holding P constant, so the pressure terms drop out. But another way to look at it, even if they didn't, would be that you have something like this. So when you substitute in, remember B is like, so you have 1 minus B. Well, B is 1 minus this thing. Well, partial V, partial J, 1 over. And so you get the ones cancel, right? And so then you'd be taking like a partial derivative of this thing. Well, this would be, even if you weren't holding it constant pressure, this would be approximately 0, right? But basically then you have this, okay? So this term goes there, this term goes there, right? Notice you have negatives in front of both of them, right? So the negatives cancel. And ultimately you're left with 1 minus K over KS. This is also Biot's coefficient. And you can make mechanistic arguments that shows that this is mechanically exact. For small strains. For small strains.
What
Yep.
K you mean?
Huh?
K.
This is the bulk. Remember, we plugged this in. We plugged this K in using generalized Hooke's law for the solid skeleton, right? So this is the bulk modulus of the solid skeleton. The solid plus the pore space, And this is the bulk modulus of the solid itself, right? And so where you get that 0.8 you were talking about is because in low permeability materials, this tends to be about 0.2, 1 minus 0.2. In high permeability materials, this tends to go away, and so you just have 1, right?